Hey, welcome back. This is the review video for test 4. I'll sort of hit on each section that I'm including in the test and give you a question poll from my math lab. So 9.1, I'm looking at questions like 5 to 10. What we were studying in 9.1 was just the idea of a sequence and whether or not it converges. We also had some technical issues with the monotonic bounded convergence theorem, but I won't be putting any of that on the test. So anyways, it'll probably be, does the sequence converge or diverge? So for example, a sub n equals n minus 4 factorial all over n factorial. So you have to answer the question, does this sequence converge or diverge? So you go to the limit, and we have to know how to deal with factorials. Okay, so there will be some cancellation here. It's always n goes to infinity. You could reuse the recursive definition, or you could sit here and literally brute force write the thing out. All over n factorial is n times n minus 1 times n minus 2. And I'm kind of looking for where it syncs up to the factorial in the numerator, and it looks like it does way down there once it gets to n minus 4. We'll have n minus 4 factorials canceling in the top and bottom, and you'll be left with some sort of a polynomial in the denominator of the expression. And of course, that's the type L over infinity, which will go to 0. So when this thing goes to 0, you'll have convergence. If it goes to any number, it'll be convergent. In particular here, it's going to 0, so definitely convergent. Okay. Remember, there were also ones that didn't. If it goes to infinity, it's divergent, but it's also, if you have like the even terms going to -3 and then the positive terms are going to 3, in that case the limit of the evens and the odds don't equal each other, so therefore it's divergent. Okay, so if I put one of those on the test, you'd have to kind of explain that just like I did in the 9.1 video. Okay, but probably just some sort of limit problem from 9.1. Okay, 9.2 then we start studying the particular sequences that we were interested in particular sequences of partial sums. There was two types we began with. The partial fraction decomposition types, and then we saw later on the geometric series. Okay, so these were great because we could actually get our hands on the nth term formula for the sum and then take the limit of that thing. We'd actually know what the sum would equal. Okay, so let me find 9.2. A lot of students are asking in particular on this one question, so let me do that question. Just give me 1 second. Number 6. So if you're lucky, all your numbers will cancel out real nicely, but unfortunately in number 6 that's not the case, right? So n equals 1 to infinity of 4 all over n times n plus 2. So this one's kind of set up nice for us. If you look at number 8 there on the right, that one's not as nice. You would have to kind of factor the denominator and then do your partial fractions on it. But let's focus on what we have. And I lost the problem already. Oh, they're number 6. Okay, so I have to do a partial fractions. So I'm going to put 4 all over n times n plus 2. That will be a all over n plus b all over n plus 2. Multiply by n times n minus 2. You get 4 equals a times n plus 2 plus b times n. And then you're going to do substitution. So let n equal -2. So 4 will equal 0 times a, which is 0, plus -2 times b. So it looks like b is -2. Then let n equal 0. So 4 will equal a times 0 plus 2, which is a times 2, which is 2a, plus 0 times b, which is just 0. And then a will equal 2. Okay? Okay. So we'll rewrite our summation, n equals 1 to infinity, as the sum of 2 all over n minus 2 all over n plus 1. Then we want to expand this thing and basically take the limit. So an infinite sum, you can think of it, it's the same thing as kind of taking the limit of a finite sum as the upper limit goes to infinity, right? So if we replace that infinity symbol with a k and write the limit as k goes to infinity, we're taking advantage of the fact that we're going to be able to find a formula for this finite sum, right? Okay, so to get the formula, what you do is kind of expand it and then let it collapse. So usually what I will do is get the first three terms and the last three terms so I can see the nice sort of cancellation. Okay, so I'll begin with n equals 1, and I'll have 2 over 1 minus 2 over 2 plus, go to n equals 2. I'll have 2 over 2 minus 2 over 3 plus n equals 3. And you get 2 over 3 minus 2 over 4. And if you don't see the cancellation pattern, you could keep on, n equals 4, n equals 5 if you need to. Okay, I just like to do the first three and the last three. So the last three, I'll need k minus 2, and then k minus 1, and then lastly k. Okay. All right, so k minus 2, I have 2 all over k minus 2 minus 2 all over k minus 2 plus 1 is k minus 1. Then 2 all over k minus 1 minus 2 over k minus 1 plus 1 is just k. And I'll have 2 all over k minus 2 all over k plus 1. Okay. So look for the cancellation. How does it seem like it looks like 2 over 2 is canceling with this guy. So this is just the normal cancellation. This one isn't even that hard. It must have been a different one I was thinking of. But I mean, there's only like 2 partial fractions in the whole. So sometimes it'll skip over a term, which is really weird. It doesn't seem like we have any of those, really. Oh, it's n plus 2, not n plus 1. I am so sorry. There is a big mistake there. N plus 2. So all of these are different. And then, yeah, we're going to have a weird cancellation. So that'll be the issue. Okay, sorry. So this would be 2 all over n plus 2. So 1 plus 2 is 3. There we go. And then this is 4. And then this is 5. And then on here, k minus 2 plus 2 is just k. K minus 1 plus 2 is k plus 1. And then finally you have k plus 2. Okay. So now I see the issue. So you see how it's not canceling really nice? There's actually like a jumping. This guy jumps over the guy ahead of it and then cancels the first term. Then the second term here would jump over this term and cancel with the first term in the next set. It would be like this guy right here. Okay, and then it's always that second term that's doing a cancellation. So this guy would be gone, and this next parentheses here, this guy would cancel ahead with something down the line here, and so on and so forth. So what's happening? It's the second one here is jumping one parentheses and then canceling with the first one down the line, right? So the second one here is jumping this parentheses and canceling with the first one down the line. This guy would cancel with this guy, and then that would be it. So it's a weird kind of, everything cancels except every other term in the first 2 terms that we look at. So what's not canceling? It's this one, this one, this one, and this one. Okay, so that becomes your the terms of your limit. So we're going k to infinity of 2 plus 1 minus 2 over k plus 1 minus 2 over k plus 2. The last 2 terms, those parts will always go to 0, and you're just left with the first 2 parts, so it would be 3. Okay. Did I put the answer in maybe? Let's see if that's right. Yeah. Okay, so that's one type. The other type is the geometric series, of course, and let's just kind of scroll through. So like number 5, you have to, well, first determine if the series is even convergent, because I could give you one that's not convergent, right? And the criteria for convergence for the geometric is basically the absolute value of r has to be less than 1. Okay, so in this case, the absolute value of r, that's the absolute value of -4/9. that equals 4/9, and I have to make sure that's less than 1. And yeah, it is. So it is convergent. Okay. So long as it's convergent then, and as long as you have the appropriate beginning, so it starts at n equals 0. If it was shifted to n equals 1, you would have to rewrite things. I don't think we had any like that in the homework though. So it's pretty straightforward at this point. Identify the a value, which is 1. The r value is -4/9, and then you plug it into the formula a over 1 minus r. So again, a is 1, all over 1 minus r is -4/9, and then this will be 1 all over, well, 9/9 plus 4/9, and that would be 1 all over 13/9, which is 9/13. Okay? And that would be your answer, which you see there. Okay. We also had the beginnings of some of our divergence tests and convergence tests, in particular, like number 11 and 12, determine if the series converges using the nth term test for convergence, or divergence rather. So number 11, we had the series n all over ln of n from n equals 2 to infinity. So what you do is the nth term test for divergence. You look at what happens to the terms of the series as n goes to infinity. If that does not equal 0, it is divergent. Okay. Okay. So looking at this form, it's infinity over infinity form. So I'm going to do L'Hopital's. So I'll have 1 all over n. So that'll be the limit as n goes to infinity of n. As n goes to infinity, that thing will go to infinity. That's not equal to 0, therefore it's divergent. Okay. Okay. Please write out your conclusion. You know, and like in the previous problem, I would kind of need to see your evidence as to why it's convergent. You need to write this out so another human could understand what you're doing, right? So here it's divergent by the nth term test. All right, 9.3, we started looking at the integral test and the p-series. So let's look at 9.3. I'll be looking at questions like 1 to 7. For the integral test, there were criteria you had to make sure were in order before you can actually use the thing. You had to make sure that the terms of the series were positive, continuous, and increasing. And it's really not that you're working with the terms of a series, it's a function, right? It's the function that represents the terms of the series. So anyways, I need a formula for 8, 10, 12, 14. You could just use your arithmetic sum, your arithmetic sequence formula, which is always a sub 1 plus n minus 1 times d. So in our case, a sub 1, 8 plus n minus 1. The difference between each term, 8, 10, 12, it's 2. So that would be 8 plus 2n minus 2, which is 2n plus 6. And usually I just guess those formulas, but at the end of the day, you know, our formula in terms of x is going to be 1 all over the 2x plus 6, right? Okay, so to use this test, you had to show that it was continuous and positive. I'm not going to force you to do that on the test. All I'll need you to show me is that it's decreasing. Okay. It is continuous on this interval. The only place it has a discontinuity is where 2x plus 6 is equal to 0. In other words, at -6/2. And that's not in the interval we care about. Because this series, what does it represent? It represents a series from n equals 1 to infinity. Okay, so I only have to worry about x values from 1 to infinity. Okay, so yes, on that interval it is continuous. Secondly, is it positive? On that interval, and yes, you'll have a positive over a positive, which is positive. The thing you'll have to prove on my test is whether it is decreasing on the interval. Okay. So again, the interval comes from the summation. It's going from 1 to infinity, and for this what you do is a derivative, right? So let's rewrite our function as 2x plus 6 to the -1. And then we'll take the derivative. F prime of x is going to be negative 2x plus 6 to the negative 2 times the derivative of the guts, which is just going to be 2. So you'll have negative 2 all over 2x plus 6 squared. Okay, that thing is clearly negative, right? It's a negative divided by a positive. A negative divided by a positive is always negative. In other words, it's less than 0, and therefore what we know from calculus, if the derivative is negative, the function is decreasing. Okay, so we can conclude it's decreasing. Okay, so I need to see on the test the derivative. I just want to make sure you still know how to do derivatives. And then you have to make some conclusion, like, is it negative? It probably will be. Okay. All right, once you've done that, then you could go to the integral test and actually find whether it's divergent or convergent. So we'll have the integral from 1 to infinity of 1 all over 2x plus 6 dx. So we have an improper integral. I'll rewrite it as a limit. I'm going to have to do a u sub. All right. So I'll sort of drop all of the characteristics, the b going to infinity, the 1, the b, and rewrite it as 1 over u times du over 2. So it'll be the limit. You can factor out the 1/2, and then the integral of 1 over u is just the ln of u. Back subbing, you get the ln of 2x plus 6. Okay, and then we want to evaluate this limit as b goes to infinity. And I know my 6's look just like b's. Let's put 1 and b into the antiderivative and then take its limit. So b to infinity of 1/2 of ln of 2b plus 6 minus the ln of 2 times 1 plus 6 is 8. Okay. The first term will go to infinity just by itself. Remember the graph of the ln, it goes very slowly, but it does keep increasing to infinity. Okay. And then you'll have minus some number, but that won't affect the overall limit. It will just go to infinity, and therefore you conclude it's divergent. Okay. All right. The next section then, I think we got into comparison tests. So you had direct comparison and then limit comparison. Okay. There were 3 steps in each type of this problem I want you to show. Okay, so let's look at number 2. 1 all over n to the 2/3 minus 1. So first I need the C or inequality where you're comparing the terms of this series to the terms of some other series which you know the behavior of. Right? And usually you could just kind of chop off parts, like get rid of the -1 there, and you have 1 over n to the 2/3. Or you can add another factor of n to the 2/3, so you'd have like 1 over 2n to the 2/3, depending on which direction you need to go. Right? So if I'm trying to prove that something's divergent, I want the series, the new series that I'm comparing it to be less than. If I want to prove that something is convergent, I want the one I'm comparing it to be greater than. Okay. In this case, if I decrease the denominator, I've increased the overall. If I make the denominator bigger, I've decreased the overall expression. So I'll have this direction of inequality. Now that'll work because the series with the terms 1 over n to the 2/3. Well, what is that? It's a p series. And you have to show me all this information. So first it's a p series. Secondly, what's the defining characteristic? P is equal to 2/3. And then thirdly, is it divergent or convergent? So if p is equal to 2/3, that's less than or equal to 1, so therefore it is divergent. Okay. So if the guy on the bottom, so to speak, is diverging, it forces the guy above it to also diverge. Hence both diverge. Okay, so you have to show me all 3 of those steps. And then the same goes for the limit comparison test, like number 7. So we have the series of 4 all over 8 to the n plus 1 from n equals 1 to infinity. So first say what you're going to compare it to. So I'll limit compare with the series 4 all over 8 to the n from n equals 1 to infinity. Okay, what is this guy then? It's a constant multiple of a geometric series. So in this case, it's geometric. The a value is 4, but the r value, the part that really tells us about the series, the absolute value of that is 1/8, and that's certainly less than 1, therefore it's convergent. Okay, so again, when you're making these conclusions, you have to say those three things. What kind of series, what's its characteristic, and what's your conclusion based off of that. Okay, so secondly then I form a limit. So note the limit of the ratio of the terms of those two series. So I have the limit of 4 all over 8 to the n plus 1 all over 4 all over 8 to the n as n goes to infinity. Rewrite that. So I got 4 all over 8 to the n plus 1 times 8 to the n all over 4. The 4's cancel. I'll have the limit as n goes to infinity of 8 to the n all over 8 to the n plus 1. You could divide top and bottom by 1 over, or you could divide top and bottom by 8 to the n and you get your answer, but this is one of those limits where you could just chop off the high degree parts. And so you'd have the limit of 8 to the n over 8 to the n, which is the limit of 1 as n goes to infinity, which will equal 1. Okay, which is greater than 0 and finite. Those were the characteristics for this thing to be convergent or divergent. Just because it has a limit in this case doesn't mean it's convergent. Okay, it's the thing that you're comparing it to that really says your answer. So if you go back and read sort of the test, it'll say you're doing this limit, looking at this limit, and if the limit is greater than 0 and finite, then both series have the same behavior. It doesn't say that they both converge. It just says that they both have the same behavior. So in our case, because step 1 it said it converged, both series converge. Okay, so hence both converge. People want to say it converges no matter what, and that's not the case. It's whatever you're comparing it to. That's, you know, if you get a limit out of it that's finite and greater than 0, the thing you compared it to, it has that behavior. Okay. Anyways, 9.5, then we get into alternating series. It'll be like questions 1 to 7, and there's always 2 steps. Basically, the first step is kind of like the nth term test, sort of, and then the second step you're trying to show that the terms of the series are decreasing. Okay, so let's look at some of these weird ones. Number 6, the sine of 2n minus 1 times pi over 2 from n equals 1 to infinity. In this case, I'd kind of investigate the terms of this series. So when n is equal to 1, I'm putting in 1 for n, right? So I get 2 times 1, which is 2, minus 1, which is 1 pi over 2. Sine of pi over 2 is what? Well, that's just 1, right? So the first term is 1, and then plus 1 n is 2. I get 4 minus 1 is 3, so I get sine of 3 pi over 2. In other words, negative 1. And then the third term, n equals 3, is going to give me sine of 5 pi over 2. So it's going to go back to 1. So I think we could basically just rewrite this series as the series negative 1 to the n plus 1. And that would be it. That's the series, basically. It's just negative, it's 1, negative 1. The first step of the alternating series test, then, is to look at the limit of a sub n. And in this case, the a sub n portion is not clear. It's just 1. Okay, that's a sub n right there. The a sub n is the portion without the negative 1 to the n plus 1. So you just have the limit of 1, which is equal to 1, which is not equal to 0 like we need. Technically, you have to do the nth term test for divergence, but if it equals a number like this, if the limit equals like 5, it'll automatically be divergent by the nth term test, because the limit of the actual terms of the series will not exist. The odd terms will be like a negative something, the even terms will be a positive something, right? Or vice versa. So once you get something like this, you can just say it doesn't converge. Okay, so hence divergent. Okay, let's look at one that actually works then. So problem 7, we had the sum of 1 over n times the cosine of n pi. Okay, I'm going to expand it just like I did before, right? So in this case, when n is 1, I would get 1 over 1 times cosine of pi is negative 1, right? So I get negative 1 plus, let's look at n is 2. So that would be 1/2 times cosine of 2 pi, which is positive 1, so I get 1/2. And then when n is 3, I'll have plus 1/2 times cosine of 3 pi is back to negative 1. Oops, that'd be 1/3. And then so on, right? So let's rewrite it, getting rid of that trig part of it and making it look like an alternating series. So I'm going from 1 to infinity, and it looks like it's just negative 1 to the n all over n. Right? It's going to give me what I got when I expanded it. That's the same thing. So it's an alternating series, and so first you check out a sub n, okay? And a sub n in this case is just 1 over n. And that needs to equal 0, and it does. Okay, so that's good. Secondly, we need to show the terms are decreasing. So what I usually do is a ratio test. 1 over n plus 1 all over 1 over n, and show that's less than 1. Okay? Taking reciprocals, I get n over n plus 1. Clearly something over something bigger is less than 1, so therefore it is decreasing. Hence, by the alternating series test, it is convergent. Okay, so it needs to pass both of those criteria for convergence. It seems like in the homework, they only like force you to do part of it, but you need to show both steps, okay, on my test. Let me just look at the homework real quick. Whoops, that's 9.6. 9.5, where are you? Yeah, so they're just having you do the limits here. You have to show both steps. You have to show the limit is going to 0, and you have to show the terms of the function, or the terms of the series, are decreasing. Okay, and I'm not going to put any of the numerical problems on there where you're doing estimations. That's homework is good for that. Okay. Let's look then at 9.6. 9.6 then we're getting into the ratio test and stuff that helps you with interval of convergence material. So 9.6, I'm looking at questions like 1 to 8, and you're using the ratio test to determine the convergence or divergence. Okay, so number 6. The series 2n factorial all over n to the 7th from n equals, I believe it's 1 to infinity. Okay, so remember for your, I'm not going to put the root test on there. The ratio test is what we use the most. So it's just going to be ratio test problems. So I'll go r equals the limit of the absolute value, replace n with n plus 1. So I get 2 times n plus 1. Factorial all over n plus 1 to the 7th, and then times the reciprocal of a sub n, which is n to the 7th over 2n factorial. Okay, so rewriting it a little bit, this will be 2n plus 2 factorial all over 2n factorial times n to the 7th all over n plus 1 to the 7th. I'm going to expand that factorial on the top, so 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, dot, 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 all the way to 3 times 2 times 1. All over 2n factorial is just 2n times 2n minus 1 times 2n minus 2, 3 times 2 times 1. Hopefully you could see the cancellation there, and then the rest of it. Okay, so huge cancellation there and there, and we end up with, and of course I lost my limit symbol, so don't be like me, always write that limit. Okay, so this is the limit of the absolute value of 2n plus 2 times 2n plus 1 times n to the 7th all over n plus 1 to the 7th. If you think about what would happen if I expanded the thing in the numerator, what would you get? You would get 7, 8, you would get a 9th degree polynomial. In the denominator, no matter what, you're getting a 7th degree polynomial. So if the degree of the numerator's polynomial exceeds the degree of the denominator's polynomial, it's either going to positive or negative infinity. In this case, positive infinity, because everything's positive. So that is the divergent case. Okay, so there were three kinds. If the R value was less than 1, it's convergent. If the R value is greater than 1 or equal to infinity, it's divergent. If R is equal to 1, you have to try a different test. Okay, so in this case, it's divergent. Anyways, 9.7, we sort of then get into the polynomial stuff, which is what I kind of our goal for this whole chapter is. And we just begin with forming polynomial representations for functions. So number 4, we want a Maclaurin polynomial for 6 cosine of pi x, and we want it to be 4th degree, and Maclaurin means it's centered around 0. Okay, so I'm going to need 4 derivatives, and then I need to plunk everything into my formula, Maclaurin formula. Okay, so you need the first 4 derivatives for a 4th degree polynomial. And you could set up your polynomial like a fill in the blank if you want to. That does not bother me. If that helps you remember things. Once we get the series, though, you're going to need that summation series notation, so just be forewarned. Anyways, f of x, 6 cosine of pi x, derivative, negative, 6 chain rule, so there's a pi in there, sine of pi x. Next derivative, negative 6, another factor of pi, gives me pi squared, cosine of pi x. Then it'll become positive because the derivative cosine is negative sine. So positive 6 pi, now cubed, sine of pi x. And then evaluate each one of these at 0. Did I skip a derivative? I am so sorry. I did. So this is the second one, this is the third, and then I need a fourth. Okay, sorry about that. So this would be 6 pi to the 4th cosine of pi x. Okay, so get f prime of 0, f double prime of 0, f triple prime of 0, f 4th prime of 0. Again, 0, you get 6. This will be 0, negative 6 pi squared, 0, 6 pi to the 4th. And then you could just copy and paste these into the blanks. And you could leave your answer like that if you want to. But like I said, you know, eventually you're going to have to make it look pretty anyways. So negative, what is this, 3 pi squared over, well, just 1 then. So it's just negative 3 pi squared, x squared. And then the last guy, 6 over 4 factorial is 24. So it would be 1/4 pi to the 4th, x to the 4th. But if you want to, you just leave it with the boxes. I don't care. All right, 9.8 then, we're working with intervals of convergence and actually applying the ratio test to these power series. So I have problems like 1 to 13. Be aware there's 3 types of these problems. There's the ones where you get, it doesn't converge anywhere except at the center. Okay, there's those. There's a kind where it converges everywhere, and then there's a kind where it converges in an interval. And I always include one where it's just a particular interval and you have to go and check the endpoints. So I want to do one of those. These typically are harder, right? But make sure you can do the other ones as well. So anyways, n plus 1 times 7 to the n plus 1, right? We use the ratio test. So I go through and replace n with n plus 1. This will be n plus 2 over n plus 2 times 7 to the n plus 2 times the reciprocal of a sub n. Okay. And then start cleaning it up a bit. So x minus 3 to the n plus 2 over x minus 3 to the n plus 1. Let the exponents cancel. You get x minus 3. 7 to the n plus 1 all over 7 to the n plus 2 is just going to be 1 over 7. And then times n plus 1 all over n plus 2. You can factor out that first term, that first factor, x minus 3 over 7, outside of the limit because it's not dependent on n. And then you have n plus 1 over n plus 2. Remember, the limits in this chapter are always n goes to infinity. Okay. The limit of that expression, n plus 1 over n plus 2, is 1. So you're just going to end up with x minus 3 over 7. And then you get your sort of figure out your radius. So you're going to put x minus 3 over 7 in between 1 and negative 1. Multiply through by 7. You get negative 7 less than x minus 3 less than 7. Add 3 to all three sides. And you get that. The radius convergence is 7. The interval of convergence, then you need to check the endpoints in the original series. Okay, so you're taking negative 4 and plugging it into the original series. So let's try that. So you'd get the series of negative 4 minus 3 is negative 7 to the n plus 1 all over n plus 1 times 7 to the n plus 1. I need to simplify this. So you could rewrite that numerator as negative 1 to the n plus 1 times 7 to the n plus 1, just using your rules of exponents. And by doing that, you get that nice cancellation, right, with the numerator and denominator right there. So you just end up with alternating series, and you could use the alternating series test on it. So firstly, the limit of the positive terms of the series 1 over n plus 1, that's equal to 0. And then secondly, use the ratio test. So you have 1 over n plus 1 is n plus 2 divided by 1 over n plus 1. Take reciprocals, you get n plus 1 over n plus 2. And as always, if you have something small over something bigger, that will be less than 1, which implies it's convergent. So at that endpoint, it's convergent. Okay, go to the other endpoint. So at 10, it's a little easier. You'll have the summation of 7 to the n plus 1 all over n plus 1 times 7 to the n plus 1. And there's a nice cancellation. And so your series is actually 1 all over n plus 1 from n equals 0 to infinity. But if you were to expand this, you would get 1 plus 1/2 plus 1/3 plus dot dot dot. In other words, you get the series n equals 1 to infinity of 1 over n, which we all know is the harmonic series, which is divergent. Okay. So in this case, the interval of convergence is going to go from negative 4, including negative 4, so you put the bracket, and then all the way to 10, but not including 10, so you put the open parentheses there. Okay. So always include one of those, but be sure you know how to do the other ones as well. The ones where you end up with an r value that's infinity, or you end up with an r value that is equal to something less than 1, right? In that case, it would be convergent everywhere. Anyways, I'm going to skip 9.9. I'm not going to put that stuff on there. 9.10 is kind of the last chapter then, and I'll just basically be asking you to create a Taylor series or a Maclaurin series, like number 5. So at the end, you got to put these in summation notation, so that might be a little challenging. Okay, so find the Taylor series for f of x equals ln x, and we want the center to equal 1. Okay. All right, so what you need to do is kind of like a pattern identification exercise. I need to do a bunch of derivatives until I can kind of identify the pattern. And that's going to kind of give me the formula for my summation. Actually, it's when I evaluate them, I really need that formula. Okay. And whatever the heck that formula is going to be my summation, right? So f of x is going to be the sum of the nth derivative evaluated at 1, all over n factorial times, in this case, x minus 1. So minus 1 because it's a Taylor series. Okay, so I really need, and what do I really need? I really need this formula for the nth derivative evaluated at 1. So I'll go to the f4 of 1, and then hopefully I can find this fn of 1 by just looking at the pattern. Okay, so here on the left I have ln x, and then I have 1 over x, which is x to the negative 1, and then I have negative x to the negative 2, so it would become positive 2x to the negative 3. Keep going until you can see a pattern, right? So this would be negative 3 factorial x to the negative 4. This would be 4 factorial x to the negative 5. Let's look at the thing evaluated then. So I'd have 0, 1, negative 1, 2, negative 3 factorial. And it looks like this is negative 1 to some power times n minus 1 factorial. Okay, so the even ones are negative, so it's going to have to be an n plus 1 right here to make the evens negative, and the odds will be positive. And then you could see if it's 2, you get 1 factorial, 3, you get 2 factorial, 4, you get 3 factorial, 5, you get 4 factorial. And then that's what goes into your summation notation, sort of. Okay, I say sort of because this first term is going to screw it up. Okay, if you want to, you could still kind of do the fill in the box technique to get an idea of how it works. Okay. And so we're putting in 0, 1, negative 1, 2, 3 factorial, and on and on. It's a negative 3 factorial, I know. So your summation notation, if you want to use this formula, it can't start at 0, because if you start at 0, you're not going to get 0 out. Okay, so you have to kind of move it over to 1 and then to infinity, and then your formula for the nth derivative of f evaluated at 1 is going to be negative 1 to the n plus 1 times n minus 1 factorial. And that would be all over n factorial times x minus 1 to the n. And then you could simplify it, and you kind of see the simplification going on here. 2 over 3 factorial is the same as 1 over 3. 3 factorial over 4 factorial is the same as 1 all over 4. So you're going to end up with the sum of negative 1 to the n plus 1 all over n times x minus 1 to the n. Okay, from n equals 1 to infinity. And make sure this thing gives you those numbers. So when you plug in 1, you just get x minus 1. You plug in 2, you'll get negative 1/2 times x minus 1. Yeah, so it seems to work. So you want to go after that summation notation to get full credit. If you're just looking for partial credit, you just want to get by so you can, get your pharmacy degree or whatever. You could just put that in, and I'll probably just take off 1 point But you know, if you want to continue on in math or something like that, you really need to start worrying about the summation notation a bit, and this would be the ultimate answer. Okay, but I know sometimes it's hard to see. So this will work. It's just I'll probably take off 1 point. Okay. All right, that will do it for the review then. As usual, thank you for watching, and I'll see you next time.